Welcome to Mars Review. I'm trusting that you live in this day and age because you're watching this video right now. Because you do, you've probably heard people talk about inhabiting Mars. You might go, why do we have to inhabit a different planet? And to that I say, whatever I put on this green screen. There you go. There's your answer. Now, if we want to inhabit, there's a problem. Okay? Mars, at its closest point,
can get as small as 54.6 million kilometers away.
The farthest
away Mars gets is
401 million kilometers.
That's over 2 times the 150 million kilometers the Sun is away from the Earth. There are 2 things I want to talk about today. One, radio waves. The other, quantum entanglement. Now this is extremely more harder, so we're going to talk about radio waves first, right? 2 things. Radio waves are electromagnetic waves, or EM waves, and so is visible light. So, as you can probably infer from that radio waves travel the speed of light. If you're familiar with the law of diffraction, the lower wavelength allows it to bend easier around obstacles and particulates in the cosmos. For today's simplicity, we're just going to use the speed of light as 3 times 10 to the 8th meters per second. And for more simplicity, instead of talking about our range of distance between us and Mars, we're just going to average out the 54.6 and 401 million kilometers to 225 million kilometers. EM waves can travel 225 million kilometers in around 12.5 minutes. If you're familiar with kinetics or have played any video game that does not require a hit scan, but requires you to lead your shots, then you know what I'm talking about. Mars is forever in a very high eccentricity orbit around the Sun, as Copernicus has so given to us. In order for us to hit Mars with a beam of information, a radio wave, we couldn't just shoot it right at where Mars is right now. Because if we shoot it where Mars is right here, say, this is a very, very simplified scenario. If I was to shoot right at Mars, it would miss, right? It would be where Mars was. So that's why you have to predict. Also, one thing you have to keep in mind is that there is innate rotation on its own axis rather than rotation on Helios, right? So if you do have satellites or receiving communication means on the actual planet surface itself, you're probably going to have to time it well, right? But this video is not meant to talk about that. This video is meant to talk about how long it would take in the most efficient way. The only thing that changes is the most opportune time to send information to Mars, not necessarily how long it will take. Now that we know about radio waves, I will talk more complicated one. Quantum physics, as far-fetched as it may seem, is the most supported physics branch. It's time to get serious, okay? Einstein came up with a little trick to how he perceived entanglement. Einstein said if you move apart 2 different electrons, right, in opposite directions, the electron's spin is determined at the point of separation. So he referred to them as gloves in a box. I have a left glove and a right glove. I have a left shoe and a right shoe, right? If I take one shoe out and move it over here and move the other really far away, from the point of separation, the left shoe has always been the left shoe. Now, what Niels Bohr said was he took into account quantum superposition. He stated that if I was to take this left shoe, move it all the way over there, and move a right shoe over here, or glove, without me observing it, without anything observing it, it is in some weird quantum state between left and right shoe. If I was to observe it, it would be a random chance. If I was to look at it and it would be the right shoe, then the other would be the left shoe. Now, this is especially useful with communication because this whole thing, no matter the distance, no matter if this is 401 kilometers, it is instant. Hopefully one day quantum entanglement could be used to more quickly communicate with aircrafts and maybe even cross-universal communication. This scared Einstein so much that he called it spooky action at a distance. Very spooky.
So what would be another option for sending messages to Mars? Why not the good old carrier pigeon? That is, if they were still alive. Now, right off the bat you might be thinking, how will the bird survive its trip? And to that I respond, it doesn't need to. It's not like the pigeon's going to be relaying the message in speech. So assuming that our pigeon would be able to fly at its maximum speed, which for an average domestic pigeon is about 148.86 kilometers per hour. It would take the pigeon approximately 173 years to reach Mars, and that's not factoring in leap years, time to eat, etc. Now obviously, this is a very impractical way for messages to be sent. However, there is a way to speed this bird up. NASA's Voyager 1 probe used gravitational slingshotting to reach an extremely fast speed that would have been impractical to attempt with regular rockets. We will be using the same effect to propel the pigeon towards Mars. For the sake of simplicity, our scenario will involve the bird performing an ideal 180-degree turn using the Earth as its propeller. So simply looking at it, the laws of physics say that the pigeon's speed after going around the Earth will be the sum of its initial speed plus 2 times the speed the Earth is moving towards the Moon, which would be its orbital speed. A little bit of quick math shows that the pigeon would now be going at approximately 216,148.86 kilometers per hour. Now, obviously there are a lot of problems here, seeing that pigeons can only withstand about 10 to 14 Gs of force. Furthermore, this would only get the pigeon going fast, but not necessarily in the right direction, towards Mars, so we would have to make sure that that was lined up correctly. Finally, it would also be necessary for the bird to hit Mars' atmosphere at the correct angle. Otherwise, it would either bounce off or burn up upon re-entry, assuming that it hasn't already disintegrated.